Okay. Let me write mathematical or algebraic representations of vectors. Now, if we, for example, have a vector like this from a point to another point, V, A, B, and suppose that A has coordinates, okay, let me see. Okay, P1, P2, P3, and B has coordinates Q1, Q2, Q3, okay? Then V can be written, can be represented, then V is represented by the triple what? So this is actually just okay, P1, no, Q1 minus P1. Okay, let me write this way, A to B, and this can be written like Q1 minus P1, Q2 minus P2, Q3 minus P3. And the justification for this can be seen as follows. Okay, now suppose this is A and this is B, okay? And V is this vector V. All right, so let's say V is this. A, B. V can be seen as follows. You see, if I draw these vectors from the origin, this one and this one, this is the vector. Suppose origin is the point O. It has coordinates 0, 0, 0. Right? This has coordinates 0, 0, 0. A and B has coordinates Pi's and Q's. Note that you see, I take the vector OA and add this to AB and I get OB, right? Why is that? Because you see, I take this vector and from the tip of this vector, I have the vector V. So the vector OB starts from the starting point of the vector OA and ends at the tip of the vector AB. Therefore, OA plus AB is just OB. Or I can write it this way, OB is just, AB is just OB minus OA. But, you know, what is this OB? It starts from this point and ends at this point. So it is just the vector with coordinates, right? This was Q1, Q2, Q3. This had coordinates P1, P2, P3. So this is just Q1 Q2, Q3 minus P1, P2, P3. So this is just Q1 minus P1, Q2 minus P2, Q3 minus P3. This is not a proof or anything, but this is the justification why we represent vectors like this, and how the algebraic operations compatible with the geometric definitions. Okay. All right. So and actually this justifies why we identify two vectors to be this as the same, right? Why we regard them as the same if they are parallel and have the same length, right? Uh, because you basically you look at the coordinate difference of the two ends of the vector. So if you have a vector like this and a parallel vector like this, if they have the same length, then we regard them to be the same. And indeed, you see, this vector can be seen as follows. Just take this vector, the vector which just joins this two, let's say W, then we have what? Ne söylemek istiyordum? Okay. V equals U. What is that? Oh, okay, okay. Here what I mean. Suppose this is the point. These are the points A and B, and these are C and D. This point here actually is nothing but A plus W. We can regard it like this. Okay, suppose I have the coordinate system here, and this is the vector A. Then this is just A plus W, C. And what about D? D is C plus U, C plus U. So it is A plus W plus U. So what is CD? CD is you take the coordinates of D and subtract the coordinates of C. So this is D minus C. Let me write it this way. So it is A plus W plus U. But actually I can also yani bunu şöyle de görebilirdik. Evet, çok da anlamı olmuyor. Yani şeyi biraz daha açıklayayım diye giriştim ama okay, forget this, yeah. Doesn't matter. I was trying to explain the notation, but I guess it doesn't have much meaning. Okay, forget it. Another notation which you are familiar actually with is the following one. In plane, in the plane, uh, the vectors uh, 1, 0 and 0, 1 are denoted as I and J, right? So in the plane, we had this vectors, 1 unit length vectors, like this one. Suppose this is the vector I, and this is the vector J, right? If these are the points 1. And in general, any vector, suppose we have a vector, let's say with coordinates A and B, I can write it like this. This is A comma 0 plus B comma 0, right? And this is just A times 1 comma 0 plus B times 0 comma 1. And we write it like this: A times I plus B times J. Okay? In tree space, in tree space, uh, we have also K ve şöyle I represents the vector 1, 0, 0. J represents the vector 0, 1, 0. And K represents the vector 0, 0, 1. So we have this. Okay. Here I have X, Y, and Z. And I, J, K are just this vectors I, J, and K. They are unit length vectors in the parallel to the XYZ axis. And any vector we, let's say with coordinates A, B, C, similar to above, can be written like this: A times I, B times J, C times K. And actually, this is good when you are doing arithmetic with vectors. For example, suppose you have vectors like this: 3i minus 4j plus 5k, and v is the vector, let's say uh, j minus or plus, okay, 7k. Then then let's say uh, 2u plus 4v is what? Well, this is just 2 times u, so 3i minus 4j plus 5k plus 4 times j plus 7k. So this is 6i minus 8j plus 10k plus 4j plus 28k. And then you just add similar terms. There's only 6i here, and then minus 8j and 4j here, so minus 4j, and then 10k plus 28k, so 38k. Or I can of course write it like this: 6 minus 4 and then 38. Okay. Uh, Definition: a vector of length 1 unit is called a unit vector. Okay, unit vector. If V is any non-zero vector, so it doesn't have a zero, let's say, okay, non-zero vector. I'm sorry, it is not the 0, 0, 0 vector. So what I mean is this. Non-zero means this. Then the vector 1 over length of V, take the length of V, and then this is a scalar and multiplied with the vector V is a unit vector. Okay? You divide your vector by the length of that vector. What you get is now a vector of unit length. Okay? Because the length of this is the following. This length 1 over this number is a lambda, is a real number. It goes out. Okay? You get this, but lambda is just 1 over this, and then you have this, so therefore it's equal to 1. Okay? Here, of course, I am using the following fact, right? If you have a vector and if you take a scalar product with a real number lambda, then this is absolute value of lambda times length of V for any scalar lambda and vector V. Yani bir vektörü bir sayıyla çarparsanız boyu da o sayıyla çarpılır. Ama tabii sayı negatifse boy negatif olmayacağı için çarptığın sayının mutlak değeriyle çarpmış oluyorsunuz. Yani bir vektörün eksi 3 katının boyu o vektörün boyunun 3 katıdır. Çünkü eksi boyunu değiştirmez, sadece yönünü değiştirir, right? Multiplying with a negative number uh, reverses its direction, but the length is just multiplied by the absolute value of that scalar. Okay. Okay, so there's this nice thing here. So let me. So if you have a, let's say, wire like this, okay. Electric cable or telephone wire, or any rope, çamaşır ipi de olur. So it has a shape usually like this. It looks like a parabola, but it is not parabola, okay? It is cosine hyperbolic x. Okay, so this is this figure is, this is cosine hyperbolic. lambda x, something like this. Sorry? We had like this, you mean? I don't know. The book uses that notation. No, they don't. Uh, it depends on the author. Okay, there is no universal, I mean, rule that you represent vectors like this. And there is the derivation for this explained. Uh, I have this written in my notes somewhere. I will okay, send, maybe bakayım bulabilirsem. Hı. Muhtemelen açıklanmıştır ama emin değilim. 120 sayfasında açıklandı mı? Ee, Şeyde yok mu peki? Liste, evet. Çünkü herkes sisteme halen dahil edilmemiş olabilir. Öyle olanları, e, yani isminiz gözükmüyorsa bir yerde, onun için ayrı bir sınıf koyacaklar. Orada gireceksiniz. Kim neredeydi o? Ee, Bulabilirsem. Hı, okay. Here it is. Yeah, so you take some part of this. Suppose the uh, curve, this curve is represented by a function y equals f of x, okay? Y equals f of x. Let Ti be the tension at this point of the wire. What is this? This is force. So it is a magnitude and direction. The direction of the force is tangent to this wire, okay? And the tension is the force, okay, magnitude of that force. So this Ti is a vector, a direction, it has a direction and a force. You may think it this way. Suppose you stand at this point and hold this wire, okay? It will pull you with a certain amount of force in a certain direction. It can be upward or downward or by some angle. Suppose this is the Ti, the tension applied to this point by the wire, okay? And this is the tension applied to this point by the wire. Yani ya da şöyle düşünebilirsiniz. Or you may think it this way. To hold, to keep this wire in this position, these are the necessary forces to be applied, okay, to the wire. And then we know that tangent theta is f prime at xi, right, from calculus. And then ti times cosine theta I is the horizontal force, right, at this point and at the other point. Horizontal forces are the same. Why is that? Because the object is not moving, right? If the forces are horizontal forces are not the same, then the wire would move, but it stays the same. It means the horizontal parts of these tensions are the same. Similarly, the vertical parts, they are not the same because the vertical forces keeps the wire hanging, right? So the vertical force should be equal to the weight of the wire. Okay, so we write also that equation. Vi is the weight of the wire. Okay, and then weight can be also computed as follows. What is the weight of the wire? You just take its length, right, and then multiply by the density of the wire, right? 1 meter has certain kilograms, so you just take that. So this is the density, and then you just multiply it by the wire, and G is the gravitational constant. Okay, and then you write this. So Vi is this expression. Here, of course, you see, you cannot compute this integral right away, but from the mean value theorem, it is what? Yani şu var ya, if you have a to b f of x dx, this is f c times b minus a, right? Where c is some point in AB. Meaning this, if you have a graph like this, the area under this is equal to the area of a rectangle at some so something like this. So you take this rectangle and the area is equal to this. So this is the average value of f on that interval. So this integral is equal to what? The length of this you know, the length from A to B times the average of the function f. Okay, so there is some C here. You just use that information over here. So this is equal to the value of this function at some point. Which point, we don't know, but there is some point like this, times the length of the interval. Okay, and then you do what? You do the following. Okay, you take this equation and divide by this equation so that you get sine over cosine, which is tangent. So that's what you do. Divide the second equation by t. So you get this gadget, you get tangents. And then you get this. And then you let xi plus 1 minus xi go to 0. So you take interval, you divide the interval into smaller and smaller pieces so that the distance between any two consecutive points goes to 0. So you take limit. When you take the limit, this gives you the second derivative of f, right? Because this is the first derivative already. When you take this quotient, you get the second derivative. And as xi and xi plus 1 goes to, if this goes to 0, it means they become the same point. But this xi was between xi and xi plus 1. So if these 2 points comes together, then xi goes to xi, right? It goes to the end point. So it means this point and this point becomes the same. Okay, right? Well, it means your function satisfies a differential equation like this. Second derivative is first derivative squared plus 1 square root times a constant. So this is the differential equation. And from the theory of differential equations, it is a unique solution, and the solution is this function, which is a cosine hyperbolic x. Okay, it is the function which satisfies this differential equation. So this is the solution. So your function look like this. Okay. Okay, I'll put this into my notes. Okay, so that you can see it. It's given here as an example, but I had done it some time ago. Okay, I'll keep it here. What else? Çamaşır ipini kapatayım. Okay, what else? We have dot product. Let me also mention that. I'll carry over that written, manuscript here. I'll copy paste it so that you will have that note over here. The dot product and projections. Okay, now dot product of two vectors in actually Rn is defined by the formula. Şöyle diyelim ki U şu olsun. U1 up to Un, V1 up to Vn. Then U dot V is defined to be the following. You just multiply the coordinates with the same indices and add them up. Okay. Sometimes we just use the summation notation, right, like this. Ui times Vi. Okay. So in R2, it becomes U dot V. Let's say this is U1, U2, dot product V1, V2. So it is just U1, V1 plus U2, V2. And in R3, it is given by let's see, u dot v. U is, let's say, u1, u2, u3. Dot product v1, v2, v3, and it is just u1 dot, sorry, u1 v1. This is usual product, u2 v2 plus u3 v3. Example, let's see, for example, dot product of, let's say, these three vectors, these two vectors, 2 minus 1, 4, 0, and 5. What is this? This is 3 times 4 plus 2 times 0 plus minus 1 times 5. So this is 12 minus 5. So the product is 0. Note that, so let me write as a remark, if u is, let's say, this vector, then u dot u is just u1 squared, right? Because u1 times u1, u1 squared, and then u2 squared and u3 squared. But what is this? This is just the square of its length, right? What is the length of this vector? Length of this vector is just u1 squared, u2 squared, u3 squared, square root. So u dot u is just norm u squared. So u dot u is just length u squared. And more generally, we have this u dot v for any two vectors uv in R2 or R3, doesn't matter. You can take Rn, okay? We have u dot v is equal to the following. Norm u times norm v, so length of the vector u times length of the vector v times cosine theta, where theta is the angle between the vectors. Well, suppose u is this vector and v is this vector. What is the angle between them? What I mean is the following. You carry one of them to the other one so that they start from the same point, because I can do that, right? Those vectors are equivalent. They are regarded the same. And then I look at this angle. Actually, you can also look at this angle, which is pi minus theta. And note that cosine pi minus theta is the same as cosine theta. So it doesn't matter which angle you take, okay? Cosine of both angles are the same. So you can take either angle. And the proof of this, okay. Bunu da yapayım. Ondan sonra bırakalım. Proof. Böyle. Okay, suppose we have this vector v and the vector u, and what is this vector? Then This is uh, okay. So whatever this is, right? V plus this vector is equal to u, right? Because uh, u starts from this point and this point, and I have here v plus this question mark is equal to u. So the question mark is just u minus v. So this is just the vector u minus v, okay? And then suppose this angle is theta. We just do the following. We apply cosine law to this triangle. What is cosine law? The square of the length of one side, let's say this side, u minus v squared, is equal to squares of sum of the squares of the other sides minus 2 times the length of these two sides times cosine of the angle between them. Okay. Well, what is this? Well, this is u minus v dot product u minus v. This is v minus v dot product v, and this is u dot v u dot u minus ya da bunları yazmama gerek yok. Let me just keep this. Okay. Here I have what? I can open this up. This is so u dot u minus u dot v. So this gadget, and then minus v dot u, and then v dot v. Here, of course, u dot v and v dot u are the same, right? I didn't tell you, but by the definition, from the definition, that u dot v and v dot u are the same because ui's and vi's can be interchanged. So this is the same thing as v dot u, right? So they are the same. So I am using that information over here. And here I have u v squared plus u squared minus 2 times u v cosine theta. But this is just u squared minus 2u dot v minus, no, minus, this is plus, right? I have two minuses, plus v squared is v squared plus u squared minus 2u v cosine theta. And now this is cancelled with this one, and this is cancelled with this one. And if you multiply with minus 1 over 2 both sides, you get u dot v. You multiply with 1 over 2 minus 1 over 2, you will get length of u times length of v times cosine theta. Burada tabii şöyle bir şey var. Üçkağıt var muhtemelen. Yani cosine law'u nasıl ispat ediyorsunuz, değil mi? Yani cosine law bu eğer bu şekilde yani bunu kullanarak ispat ediyorsanız o zaman hani yumurta tavuk hikayesi olur. Ama birini kabul ederseniz diğerini yapabiliyorsunuz. Okay, let me stop here. Tomorrow I'll continue.